All right, so what we have here is a tool that is going to allow us to test the predictive power of the flat Earth model. Okay, we're going to use it to predict sunrise and sunset if the Earth were flat. Now, I've got this laid out according to the azimuthal equidistant projection map. And here's the reason why. Because there's only really, if you consider the track that the sun makes when viewed from the Earth, only the AE map and the globe fit into the observable events. And what I mean by that is, on the equinox, the sun tracks a circle over the Earth, tracks a line along the equator. So anybody standing on the equator will see the sun pass directly overhead. So the path along the Earth's surface that is perpendicular to the sun on the equator, that path we call the equator. Uh, and then on December 21st or thereabouts, when the sun is at the southern tropic, that marks the most southern track of the sun. So that would be here. Okay, and that's the northern tropic right there. So if you take that circle, the equator, and you go to the center, we call that the North Pole. Okay, and regardless of whether the Earth is flat or spherical, on the equinox the sun tracks a circle, and at the center of the circle is the North Pole. Okay, those are just the way we describe the way it's described as viewed from the ground. And then you draw the latitude lines equidistant from the equator to the North Pole, and you have them all laid out every 10 degrees to north, all the way to 90 degrees north. Okay, and no other model that you're going to come up with is going to match those observations. Um, People have suggested a dual pole model for the Earth to try to account for the south celestial pole, and that's it's obviously never going to work. There's no way you can make a model like that work. So the only options you've got are this, the AE map, and the globe. All right. So in order to test the predictive power of the AE map with regards to the flat Earth, you take this diagram, which I've made up, and I'm going to print this diagram out in black and white and provide it as a printable either PDF or a JPEG with the Reddit post that I'm about to make. Okay, so that you can do all this for yourself, for your location, for your specific location, so that you can verify the sunrise and the sunset and where the sun is rising, and determine for yourself if the model stands up to scrutiny or not. So, first thing we're going to do is I'm going to take this grid. Okay, now this line right here, this line represents the azimuth of the sun. Okay, and so what we need to do, the longitudes, as far as this model, don't matter, because we're not using this to show our relation to the rest of the Earth. We're using this to show our relation to the sun's track. Okay, so I'm going to go to Wikipedia, which I've already done, and I'm going to show. Okay, so I've already looked up Houston, Texas. That's what I'm going to do this model for myself, and you can follow along with me. And so I've searched up Houston because that's where I'm closest to. And so I've searched up Houston in Wikipedia, and here are the coordinates of Houston. 29 degrees 45 minutes north latitude. And you'll see that when you start to draw this grid out by hand, if you print it out and actually take the time to print it out and start measuring it, you'll see that a quarter of a degree is pretty trivial. You're going to see when you start using the grid to predict where the sun is and where it's supposed to be, you're going to see that we're dealing with a lot bigger discrepancies than just a quarter of a degree. So if you're within a degree, you know, on your protractor, whatever you're using to measure your angles with, you're going to be close enough. All right, so we're just going to round that off to 30 degrees. 30 degrees north latitude, that's the location of Houston. So what I'm going to do, I'm going to go back here, and I'm going to mark, I'm going to put a little circle here, 30 degrees north latitude, right along the azimuth line. Okay, that's what you're going to want to do. Mark your location along the azimuth line. Okay, so here's 30 degrees north latitude, this circle right here, and where it intersects the sun's azimuth, right there, that's your location. Okay, now I'm going to make a little line right here for due east. Okay, so from my position in Houston, if the Earth were flat, this heading up this way, this is due north, this is due south down here, and then this line here, this is going to be due east. Okay. Now, the next thing I'm going to do is I'm going to go to timeanddate.com because they have very accurate tables of sunrises and sunsets and all sorts of good data. Okay, now I'm making this video on February 20th, 2017. As you can see, that's highlighted right there, February 20th, 2017. And I've already set the location to Houston in the website. Okay, so this website shows for a viewer in Houston, and we're going to use tomorrow as our example. On February 21st, these are the times and the angles and everything you need to know to predict and to verify for yourself. If you're in Houston, you can use this chart. If you're somewhere else, you're going to want to look up the chart for your location and verify all this for yourself. But for a viewer in Houston, here's let me show you the key points we need to be looking at. Right here, this is solar noon, 12:35 p.m. Okay. Now, over here, it shows the length of the day is 11 hours and 20 minutes. Half of 11 hours and 20 minutes is 5 hours and 40 minutes. Okay. So, sunrise, 6:15 p.m. You can see sunrise, 6:55 a.m. Sunset is at 6:15 p.m. And solar noon, that's the azimuth, that's the highest point that the sun will be in the sky, due south, is at 12:35 p.m. Okay, so if you subtract 5 hours and 40 minutes, which is half the day length is 11 hours and 20 minutes right here. If you subtract 5 hours and 40 minutes from 12:35 p.m., you will get sunrise, 6:55 a.m. If you add 5 hours and 40 minutes to 12:35 p.m., you will get the sunset of 6:15 p.m. Okay, so that's a little verification that we can use to check. You split this in half, and you measure it off the solar noon, and you should come to these two times, and that tells us that we've got a good that we've done our math right. And the reason we do that is because you're going to need it for the grid. You're going to need to know what half the day length is, because you need to know where on the grid the sun is going to be at sunrise and sunset. Okay, so let's go back to the grid. Okay. And so, I'm sorry. One more thing we need from sunriseandsunset.com or timeanddate.com. What we need is you go to this page here. You can see the the address that I've got plugged in right there. You can also find it from, if you go here, I'm trying to remember how you navigate. I think you go to this tab right here, and then you go down to this right here, and it brings you to this page. And so for tomorrow, let's see. Well, and I've already actually, let me load up the one that I've got because I changed the time on it, but it doesn't matter. 12 hours and let's see. So on 2/21, which is tomorrow, 12 hours and 16 minutes in, you've got the sun is at its zenith, which means this is the point on the Earth that the sun is passing directly overhead, 10 degrees south latitude. Okay, so that's the track, and it takes this 12 hour, it really doesn't matter because what you're looking at, if you start fiddling around with this, changing this, advancing this by 12 hours, 24 hours, you'll see that it moves like 15 minutes a day. It's like a quarter of a degree a day. So for all intents and purposes, the sun stays on a 1 degree track for, 3, 4, 5 days at a time. So the sun's track tomorrow, information we need, 10 degrees south latitude. So let's go back to the grid, okay? And you'll see that I've already marked this circle yellow just to give us an indication of where the sun's at. So that is the track. If the Earth were flat, that is the line over which the sun would be tracking. Okay, anybody standing at 10 degrees south latitude would see the sun pass directly overhead today and tomorrow. It will happen. Okay, whether the Earth is round or flat, that statement is true. If you're standing at 10 degrees south latitude, the sun will pass directly over your head today and tomorrow. Okay, so so from your point of view, you being or from the point of view of a viewer in Houston, right here, which is 30 degrees north latitude, you look due south. This is the position right here of the sun's zenith, which is 12:35 p.m. Okay, and then so what we want to do is we want to find where the sun's going to be at sunrise. Okay, here's where the sun will be 6 hours after zenith, and then the sun's going to follow this track all the way up to here. This will be solar midnight, and then it'll be over here, 6 hours later. But what we found, which we've already done our math, is 5 hours and 40 minutes before the zenith is the sunrise. So, and I've already marked out these over here to make it easier on you. Here's azimuth minus 6 hours, okay? And each of these is 15 minutes. So you can see I've put a couple little marks here already. This is 5:35 and this is 5:40. So this is our mark. That's 5 hours and 40 minutes before the zenith. So what I'm going to do is I'm going to draw a line from the center of the sun's, from the North Pole, and to right there. Okay, and this line represents the progression of the sun along this track at sunrise. Okay, so this is the sun's actual position at sunrise along the track, 5 hours and 40 minutes before the zenith. Okay, 5 hours and 40 minutes, it'll be right here. Okay, at 12:35 p.m. Okay, so note that this is not an actual time on your clock. This is the time measured before and after zenith. Okay, because it's sunrise was at 6:55. Is that right? Wait a minute. Yeah, 6:55 a.m. was the sunrise. Okay, which is 5 hours and 40 minutes before the zenith. All right, so here's you, or here's a viewer in Houston, 30 degrees north latitude, and here's the sun's actual position at sunrise. Okay. Now, one more thing that we didn't pick up we're going to go back to timeanddate.com, is right here, right there, 101 degrees. That is the angle that you will view the sun if you're in Houston, Texas on February 21st. 90 degrees being due east, 101 degrees therefore is 11 degrees south of due east. Okay, so, and this is something you're going to need to verify. You're going to have to get your compass, go outside at 6:55 a.m. and verify it, or for whatever time and place that you're at, you need to verify for yourself. Okay, but for a viewer in Houston, Texas, the sun will rise 101 degrees, which is 11 degrees south of due east. So, going back to the model, what I'm going to do is I'm going to take this line and I'm going to rotate it 11 degrees south of due east. Okay, so this right here, this is the actual direction that you're going to see the sunrise from Houston, which is right here, 11 degrees south of due east. I'm going to make another line for due east, okay? And then I'm going to make a line for the sun's actual position, which we found it is right here. This is where the sun will be at sunrise. I'm sorry. This is the sun's, this is the point over which the sun would be, or is rather, if the earth is flat, you would be viewing the sun at this angle. Okay, but in fact you're viewing it from this angle. You will be viewing it from this angle, 11 degrees south of due east. Just to show that I've got the angles right. Okay, there's 11 degrees south of due east. Now the angle here is 27 degrees north of due east. So you've got a 38-degree discrepancy in where the sun is at and where you're viewing it from. So if you believe that the earth is flat, then you have to believe that there is 38 degrees of refraction on that day. 38 degrees, and it's going to change from day to day. If you do this every day, you'll see that it changes predictably. Okay? So it's not even consistent. You know, you can't say that there's 38 degrees of refraction every day, that it changes predictably from day to day. 38 degrees of refraction. And yet, the flat earthers say that when they're measuring along the water and they're able to view something slightly over the edge of the water, that 1 degree of refraction along the water's edge, of vertical refraction, doesn't exist. They completely dismiss that. But they will allow for 38 degrees of horizontal refraction to allow for the fact that the sun isn't where they think it should be. So it's completely nonsensical.